All right. So in the book, chapter sections 23.8 is super interesting. Uh, it actually, in terms of the things that we know about, right? Inductors, resistors, capacitors, and transformers, describes how circuit breakers work, how three-prong outlets work, how GFCI switches work, um, and really, I think that's just really fascinating. Everybody should have a basic knowledge of this. Unfortunately, our time is short, so I'm going to leave you to read that on your own. I hope that you do. Similarly, um, there's not a whole lot of meat in section 23.9, like calculating meat that we can do. I definitely, like, of course, you definitely have to read it and you have to know what's going on, right? So the idea is that just like we have resistance, which resistance is how well does current flow. We know about capacitance, right? How well does charge get separated? And we now know about inductance. In class and in textbooks, there is a tendency to view all three of these things as separate phenomena, right? R for resistance, C for capacitance, L for inductance. There's this tendency to say, well, all of these effects are separate, but that's definitely not the case. Any element that you put in your circuit has some of each of these, right? The question is what dominates and under what conditions. And also, how do we separate them out, right? So even if we draw a simple circuit, right? So voltage source, capacitor, inductor, resistor. Even though in my diagram I'm drawing three different things, in reality, all three of those, like capacitance, resistance, and inductance, could be part of the same circuit element. I'm just separating out the effects of resistance, capacitance, and inductance one at a time. Because that's how we do in physics, right? We strip things down to a simpler case, and we see how that works. There is a lot of kind of symmetry between voltage and current. So our basic relationship between voltage and current is mediated by resistance, right? That's Ohm's law. Clearly, we would like to extend that because we know about more than just resistance at this point. Have you all have you already done your lab about RC circuits? Is that in the past, or is it something that you haven't done yet? And Gregory, that's exactly right. So you similarly, like with batteries are a voltage source, but they do have a small internal resistance because they're made of real materials. But the resistor and the voltage source are actually the same piece of equipment, the battery. All right, current lab. Excellent. So in RC circuits, right? We'll start there. And we'll consider DC voltage, right? Direct current. There's no time variance in our voltage yet. When we turn on our, so if, say we open up the circuit, right? It's not connected. There's no charge on either plate of the capacitor. And then when we turn it on, we flip the switch on, we connect the circuit, and current tries to flow through the resistor, through the capacitor, except the capacitor is actually a gap in the circuit, right? It's a physical separation. Current can't flow through the capacitor. So instead, we get charge build up, right? Charge builds up and builds up and builds up. And so in the lab, what you're looking at is you're looking at how fast the charge on the capacitor builds up when you close the circuit, and of course the speed at which that the charge builds up is also the speed at which the voltage builds up. Dallin, how is that different from a battery or the voltage source? Can you be more specific?
We said the capacitor basically is like a dam that builds up the charge, but the voltage source already has a charge and it's releasing it along the wire until it hits the dam.
Yes. And the charge will continue to build up on our capacitor, on this dam, until the voltage across the capacitor is the same as the voltage across your source. Does that make sense?
So is it like just a little battery? A rechargeable battery?
In some senses, yeah. A capacitor is a way of storing electrical energy. And you can store like a large amount of electrical energy in a capacitor. You store and that energy is stored by separating charges and creating this electric field. So a battery, right, stores electrical potential energy in the source, as chemical energy, right? If we're using like a chemical battery. But a capacitor stores that energy directly as electric fields. Does that make sense? Does that answer your question, rather?
Yeah, thank you.
All right. So your lab gives this prediction of how the voltage across your capacitor will change with time. It looks a little complicated. but it's actually it's not too bad. So the negative exponential function, right, e to the minus x, looks something like this. It starts off at 1 at 0 time, and then it kind of decays. And at long times, it's basically 0. So the reason why this works, so at time t equals 0, so the moment you turn on the circuit, t is 0, e to the minus 0 is 1, and so this thing in the parentheses is 1 minus 1, well, that's 0. So as soon as you open the circuit, you have no voltage on the capacitor. It hasn't had time to charge up yet. That makes sense. At very long times, t to the minus infinity is like 0. So in the parentheses, you get 1 minus 0. That's 1. So at long times, the voltage across the capacitor should be the same as the voltage that your battery is outputting. So in the limits, those make sense. Your lab is about measuring the in-between times and seeing how good it is at predicting the voltage at in-between times that aren't 0 and also aren't infinity. Again, this is for charging. For discharging, we're going to go in the opposite direction. We start at full voltage and then we come down, and at long times we get 0 voltage. Where this R and C in the exponent is literally the value of the resistance of this resistor and the capacitance of this capacitor. And R times C is the time constant. So T over RC is like how many time constants you've let the system relax. When I taught this lab, by the way, I used to say that this lab is the modem restarting lab. So how many people have ever called into Cox and said, you know, my internet's not working, and the first thing they say is, turn it off, wait 30 seconds, turn it back on, right? Has everyone had that experience? Why do you have to wait 30 seconds before you turn it back on?
So the capacitors can recharge.
Well, yeah, so discharge, yeah, that's exactly right. So you turn it off, and you're not feeding any fresh power into it, but the capacitors still have electrical energy stored. You need to give them a chance to discharge. So the system is fully off before you restart it. And this is why. This is why 30 seconds. 30 seconds ends up being 3 time constants for the resistor and capacitor in that circuit. And that's why 30 seconds. Because after 3 time constants, you have essentially no voltage left on the capacitor. Right? Because e to the minus 3, right? That's 1 over e cubed. Right? And this is something like 4%. Okay. So when we say that our battery is at 100%, can we say that it's at full voltage? So So the behavior of batteries are a little bit outside the scope of this class, um, but yeah, batteries have a nominal voltage. So like the lithium cell on your phone has a nominal voltage of like 4.2 volts. The less charged it is, the less voltage it actually puts out. And long ago, the way that your phones predicted how charged they were was just by monitoring the exact amount of voltage they put out and looking up what percentage charge that was associated with. But anyway, that's a little bit of a tangent. But short answer is yes, batteries also have a behavior like this. Yes, that applies to all batteries. All right. So that's RC circuits, and that's your lab for today, or this week rather. There's also RL circuits. So what if our circuit was a voltage source, an inductor, and a resistor? So remember what we said about Faraday's law, right? The induced voltage is equal to the change in the flux over time. So you've got this inductor, and we draw it like a coil of wire for a reason. Usually they are physically coils of wire. So if they've got a current running through them, that means they've also got a magnetic field running through the middle of the solenoid. And these inductors are analogous to capacitors, right? Capacitors store the energy in in electric fields. Inductors store the energy in their magnetic field. So they are both ways of storing electrical energy in fields. But the inductor, since it's got this B field running through the middle of it, right? When it's on, if you try to decrease the current, say by turning it off, the decrease in current will cause a decrease in the B field, but a decrease in the B field causes a decrease in the magnetic flux. The decrease in magnetic flux will cause an increase in voltage. So inductors resist your attempts to turn them off. And you get a really similar thing you did with the RC circuits, except instead of voltage decaying as a function of time when you turn the circuit on or off, it's current that charges or decays as a function of time. So as you are charging, so when you first turn the circuit on, looks very similar, right? So capacitors, for a capacitor, it takes time to change the voltage on a capacitor. And for an inductor, it takes time to change the current. Right, and this is charging. And if you're going to discharge, exactly the same form just with voltages replaced with currents. Questions or comments here? You're not actually going to do an LR circuits lab. There's one in your lab manual, but I don't think you're going to actually do it. What you will do is an RLC circuit. Why do we subtract? Why do we have the 1 minus? Okay. The reason why we have the 1 minus is actually because at t equals 0, e to the minus t is 0. Or sorry, wow. Not e to the minus is 0, it's 1, which means that 1 minus e to the minus t over LR is 0. And that's the behavior we want, right? Or the behavior that we physically observe. So at time 0, there is no current through the inductor. So we have the 1 minus because, basically that's what it takes to replicate the behavior we see. Does that make sense? All right. So that's the behavior of RC and RL circuits under direct current. Our real goal, though, is to analyze circuits that have all 3 types of components and that are under alternating current. Right, so if we're under alternating current, then if we plot voltage versus time, we get, say, a sine graph. This black curve is for like the circuit as a whole, or maybe is your input voltage. Over all of the components that are, say, a capacitor, the voltage curve across a capacitor looks a little different. And I had a picture that I wanted to show, but now it appears to, I appear to not be able to find it. Oh well. The voltage in the capacitors is going to be behind the input voltage. So if the voltage in the, going into the circuit peaks at this point, the voltage across the capacitor will peak later. And again, that's because it takes time to charge the voltage on a capacitor. if instead we made a graph of current versus time, and we're getting alternating current in, say this purple is for a capacitor. The current in through across a capacitor will be just fine, but the current across an inductor, right? It takes time to change the current across an inductor, so the current across the inductor will be behind. And when you do your RLC lab closer, 2 weeks, one or in a week or two, you'll be measuring, right, these lags, which I think is pretty cool. So for direct current, we talked about resistors or resistance. And again, it would help if I could spell. When we have complicated circuits using AC power, there is an analogous idea, right, which is reactance. Or impedance. And what I'm about to show looks a lot like the Pythagorean theorem, and it looks that way for a reason. So the total impedance of a circuit under AC current, there is a certain amount of impedance because of the resistance of the circuit. There is a certain amount of impedance due to the capacitance in a circuit. And there is a certain amount due to the inductance of the circuit. Oh, hold on. I lost my pen. Let me start off doing these separately. Before we talk about it. So impedance, we use the letter Z for it traditionally. And then for reasons I am not fully sure of, instead of using Z for the reactance of capacitors and inductors, we use the Greek letter chi. Where here, F is the frequency of the current that we're trying to drive through the system. So, okay, so this form is actually pretty important for low frequency electricity. That is, in the limit, it's direct current, right? So direct current has a frequency of 0, right? For a frequency of 0, the capacitive reactance goes to infinity. That is, you can't sneak DC current past the capacitor, which makes sense, right? Capacitor is an actual gap in the circuit. Direct current does not get through. On the other hand, the inductive reactance low frequency current gets through an inductor just fine because, right, inductors take time to change the current across them, but if you are only slowly varying the current, that's fine. It's if you want to vary it very quickly that you get into trouble. And then the total behavior of the circuit with with time varying current. Right. The actual resistors, play a role in how difficult it is to force current through a circuit. But then the inductors and capacitors also play a role in how difficult it is to force current through a circuit. The end result being that you get a kind of generalized version of Ohm's law, where the voltage as a function of time through the system is going to be equal to the impedance times the time varying current. Okay. Questions or comments? Your brain hurts. I know. We're almost to the end. I want to do just some problems to kind of solidify the stuff that we've talked about. All right? Because that is, it sounds pretty abstract, and trying to understand it in the abstract is quite challenging. But using it is pretty easy. Here, from the book. At what frequency does this relatively large capacitor, 80 millifarads, have a reactance of 0.25 ohms? And when we say it has a reactance of 0.25 ohms, we mean that that whether you've got a 0.25 ohm resistor or an 80 millifarad capacitor, the effect on how hard it is to shove current through the circuit is the same. So, the capacitive reactance is given by 1 over 2 pi frequency of the current, capacitance of the capacitor. And we are trying to design a situation where this reactance is actually just 1/4 of an ohm. The frequency at which that will be true we just solve for f. Alright, so we have 1/4 times 0.08, that's going to be about 0.02. So and 2 pi is about 6.28. Right, so this whole thing is what? You had 7.96? Yeah, that's where I was headed to. I was going to say about 9, but you're calculation is better. So that's a pretty low frequency electrical current. Right? Remember that the electricity we get out of the wall is 60 hertz. So yeah, this is relatively slow. Let's see. Let's grab another one of these problems. We're going to pull one of these. This is from the motional EMF. Right, so back to inductors, which I know we talked about in the long ago time of like an hour ago. All right. So how fast does this bar have to move in order to produce 1 volt of EMF? All right, so here we've got basically what we have is a loop inside here, right, where current is going around this loop. And this is one of those weird situations where we get induced voltage by changing the area of the loop, right? This bar is sliding to the left. Or sorry, this bar is sliding to the right. So the induced voltage is equal to the change in the flux over time. The flux is the number of loops times the area of each loop times the strength of the B fields times the cosine of the angle between them for B fields that are not already perpendicular to the loop. All of this over time. So in this particular case, we have one loop, and that's not changing. The B field is always constant. It's a constant 1.5 Tesla field. The B field is perpendicular to this loop, so cosine of theta is 1, and it's not changing. So all we have then is the change in the area of the loop with respect to time. So far, so good. So the rod's length is 30 centimeters. We're going to apply that in a minute. Since we have a square loop here, the area is actually the length times the width. The width is not changing. the width is a constant 30 centimeters. So we're just left with the change in the length with respect to time, where the length is here. No, you're right. You're right, Martin. The negative sign, though, is just going to tell us about the direction. So it's not going to be super important. This question is equivalent to asking like what the magnitude of a vector is, or the direction we don't necessarily care too much. But you're right. I should have carried the negative sign. All right. So the change in length of this thing with respect to time, how do we get at that? What is that? Right? How fast is the length of this rectangle increasing? Well, the speed at which that length is increasing, that's exactly what we mean by the velocity of that rod. Here, let me put hats on this voltage here. So the voltage has hats, the velocity does not. And the voltage, I already know, is going to be 1. Okay. Questions or comments on this problem? Are there no questions because it's perfectly clear, or because people's brains have turned to mush at this point in the afternoon? That's fair. So even though we've talked about a lot of different applications, right? There isn't that there isn't that much that we actually have to remember that we can do calculations with. So the two things that are really important to be able to do calculations with is Faraday's law and the capacitive reactances that we did a couple of boards ago. In fact, maybe a short review is in order. Here's what we've learned in the last couple of weeks. Magnetic fields cause forces on charged moving particles. Since currents are just collections of moving charges, this force also applies to wires that are carrying currents. We went through a couple of specific details, like the Hall effect. But that's not like the thing that we want to focus on, right? If we can exert force on a piece of wire, we can exert torque on a loop of wire. This is essentially everything that we learned last week. This week, we learned that not only do magnetic fields produce forces on charged particles, but that moving charged particles can create magnetic fields. We learned really just one specific example. Right, the B field created by a wire where here if we have a wire like so, then at a distance r from that wire, we will have a B field that is curling around the wire. Right? And the direction of that curl is because of the right-hand rule. Once we have a way of producing a B field through a current, this can actually apply to everything that we learned last week. So whether it's a B field that's produced by a permanent magnet or a B field that's produced by a piece of current carrying wire, the effect is exactly the same. So moving charged particles can create B fields, but the maybe more surprising result is that changing B fields can actually create a voltage. If you put together these two things here, right? The current produced by the B field produced by a current, combining that with voltage produced by a changing B field, you get all sorts of things. You get transformers. you get generators. You get motional EMF. Not emotional. Emotional is what I get when I watch Electro Boom. This is motional EMF. What does mu stand for again? So mu is the universal constant related to magnetic fields. So for electric fields, we had the permittivity of free space. This mu is the permeability of free space. It's a constant, so it's one that you'll have to look up when you need to use it. But yeah, the magnetic constant, it's about 1.26 times 10 to the minus 6. All right. So this blue and green stuff here was the more theoretical ideas in the chapter we covered today. The more concrete ideas that we covered today is the behavior of inductors, and specifically the behavior of circuits under AC, where capacitors provide a resistance to current equal to 1 over 2 pi Fc, and inductors provide a resistance to current that is, not 1 over, that is 2 pi Fl. Okay. So this is basically everything we learned in the last 2 chapters. Anything that's not on the board is just a special, like a nice application of one of these bits of knowledge. It may please some of you to know that today is the end of our electricity and magnetism section. Starting next week, there will be something completely new. You were starting to hate it a tiny bit less. All right, so with that, I would like to share one more Electro Boom video before we bid him adieu.